Hi everyone, this is Banu Köse. I'm going to talk about building a common language between engineers and clinicians with the help of my experience in last 10 years. Glad to be here in 3D Magnetic Printing Conference, and thank you, Peter, for inviting me. And but it doesn't move when I try. Yeah. Now I am in Turkey, in Istanbul, and it's a well-known place of Istanbul. Maybe audience can feel familiar when they see that. This is Hagia Sophia and Blue Mosque. And today I'm going to talk about my research field and then my experience and my journey. As a result of my journey, I want to talk about my suggestions for more efficient solutions in multidisciplinary environments. This is Medipol University. I am an assistant professor in Medipol University. Medipol University has 5 hospitals, many institutes and departments. So we have chance to work multidisciplinary environment, but it was still not enough, even we were at the same environment, at the same university. So this is my lab. We are focusing on 3D objects, actually virtual 3D objects and virtual simulations like virtual device performance tests, blood flow dynamics, or custom implant designs, surgical designs, and of course, patient-specific surgical planning. I will talk about one of my study here, and I will come up with my suggestions related to 3D printing and creating a common language between clinicians and engineers. So this is the main problem when we are trying to solve a problem on healthcare system. So as you know, congenital vascular malformations or vascular diseases, circulatory system problems are very important because affects significant portion of the populations. So I focused on congenital, newborn abnormalities of cardiovascular diseases. This is a coarctation on aorta. So I focused on obtaining that DICOM image, it obtained from MRI and CT devices, creating segmentation to obtain virtual replicas of the anatomy, and of course, creating our own image processing softwares and using finite element modeling, creating some new codes for simulating blood flow and also some mechanical issues related to soft tissue. Then trying to understand the physiology of the hemodynamic environment and also creating the optimal solution for congenital repairs. So this was the virtual model we obtained from using DICOM data like MRI and CT, multi-slice data from multi-slice data sets, and we applied computer-aided design tools to manipulate this data, just trying to mimic what we are doing when we are in the operation room. With the same steps, we obtained patient-specific patches. This is a three-dimensional patch. This is another patient, and also we tried to mimic mechanical answers of endothelium under the load. Like after an incision, what happens to an endothelium? We tried to mimic it by using numerical mechanical simulations. And after that, the main plan was mimicking blood flow using Navier-Stokes equations. We tried to mimic the blood flow simulation in that geometry, in that volume, patient-specific volume. Then we could obtain the blood flow simulation for preoperative data of the patients, like you see the coarctation and the turbulent flow. And this is a virtual repair, and you can see how smooth it is. It's a linear streamline. So we could compare pre-operation and post-operation real data of the patient in terms of velocity, washer stress, and pressure. And also we could compare virtual repairs by applying computer-aided design. We obtained them by using computer-aided design tools. So let me go. And when we understood that we can do that, we can simulate blood flow and we can validate ourselves, and it helps to understand or to obtain the optimal solution for a disease, for a treatment. So we thought that we can create some patient-specific materials, because we have that kind of segmentation skill. We have a skill of in silico medicine, like simulating, numerical analysis for mechanical and flow dynamics. And also by using them, we can create new generation devices like this. This is a patient-specific graft, for example, a buffle for a newborn patient with hypoplastic left heart syndrome. So we could create some virtual devices with different diameters, lengths, and shapes. So we could compare them by simulating blood flow distribution, and we could find which would be beneficial for that, for only this patient like this. These are the chosen ones. So this took us to 3D printing in that, because we created this, and we could apply this to the patient after creating them. At first, we used some models, prototypes. Then we started to create them by using bioprinting. So this is a scene from our 3D printing lab in Istanbul Medipol University. So yeah, and then we understood that we can design something by using patient-specific models, and we can compare them by simulations. Then we can obtain physical replicas of them for prototyping. Then we can go to the bioprinting, or using some fibrous and polymer mix of the materials for creating materials, biomaterials for patients. So of course, we could apply this to orthopedics, for surgical guides or prostheses, for physical rehabilitation departments. So we can, if we have that kind of a skill, we can apply this. So we are using engineering methods. We think that there is a clinical need, and we are creating some solutions. But actually, this is not the real world when you want to create a product, because we should consider more of this. Okay, we have a tool. It works, but it is still not enough, because for an engineer, an engineer and a clinician has a question, and we are trying to solve something to help to healthcare professionals, and we are creating a solution, but the questions are different. Clinician has a request to solve a problem faces in his or her daily routine, or we think that they need something, or they think that they need something. But for an engineer, we are different. Like we can think also, if we have that kind of a tool, like virtual tool, we can say that, what if this device was made by another polymer? So we can try to create that, even thinking to apply to the hospital in the end. Or we can ask this, why don't we produce more unique mechanical support devices for pediatric patients, for example? So this is a question, and we can perform that. We can, if we face with something in the hospital environment as a field or service engineer, we can try to improve something, but still we are thinking from different fields. Even we are at the same environment, in the same hospital, in the same university, this is like something like being in a cloud, in a limited place. But actually, there are something more in the real life, like trials, standards, regulatory systems, and legal systems, patents, ethics. And also manufacturing is not so easy as we imagine. And also, we even engineers and clinicians don't have an idea about business. We don't have business skills if we are not educated on that purpose. So our plan was here in Medipol University, creating a new environment for engineers and clinicians. So we have, the same questions, same items, but they are unique to us. So we wanted to start to think about them from the beginning. I mean, starting with undergrad students, then they are learning everything at the first moment. So we gave the questions, they were all together, they were in the same environment, and this time they created new questions, different from the previous ones, and they were under the same roof. So the questions were different and the solutions were also different. So we created a course called Clinical Engineering, there were medical students and also engineers, engineering students. So they created their own projects when they were in the same environment. I mean, the mixed undergraduate students went to clinic together, and medical students learn coding. They designed, for example, designed a biopsy needle together in the same teamwork. So when they were learning their own discipline, they were at the same. They were also trying to solve a problem at the same time in another lab. So it was a different hybrid environment that it helped us very much when they were at the same team. So in the end, we saw that most of students were focused on surgery projects. They come up with ideas related to surgery, like cardiovascular surgery and orthopedics were the most famous ones for the students. Actually, we assumed that at first it would be radiology, but it was not. Surgery was the most preferred one for the projects, with multidisciplinary hybrid projects. Second was reducing workflow in hospital, in clinics. The third was optimal design solutions for devices and some medical components. And the other was deep learning. Actually, at first we thought that deep learning would be the first one. And in the end, we come up with 4 startups, 12 grants, and 3 international collaborations with students and with our university. So actually, most of the time, the engineering students are learning the components of the devices, circuits of the devices, and they face with the troubleshooting issues at the hospital when if they work as a field engineer or a service engineer. But if they have that kind of a knowledge before graduation, they are coming up with new different solutions by using different components, and because they know the purpose of the treatment, the diseases, the physiology, and the limits of the hospital, the procedures. So they can create effective materials, or they can look for more solution-based. This was very helpful for us. And these are my students, which are in the hospital, and they created some three-dimensional objects, replicas before surgery for ventricle septal defect repairs, and double outlet track ventricle repairs, and also for some students from anesthesiology department. And if the idea was combining the methods of engineers and clinicians, just all the tools what we are using in our daily routine, and in the end, we thought that the main plan of the innovation of healthcare should be related to this interdisciplinary study, because the keyword was here was using the same language. So if they start earlier, they can learn more, and they can have understanding about terms, procedures, limits. So sometimes a clinician can ask a question from an engineer to create a magic if he or she doesn't have an idea about the engineering method. And also an engineer can create something crazy. So if we start to use same language, we saw that there are more beneficial results in the end. That's why there are some people thinking the same thing as me. I met Clinician Engineer Hub 2 years ago, and now I am the research lead in Asia of Clinician Engineer Hub. So the main plan was bringing together clinicians, healthcare professionals, and engineers to think out of the box, thinking different from traditional methods. So Dr. Neil Sharma created this, and we had many events. Actually, we have, I think, one event for each month. So one was, for example, clinical hacks was for medical students to show coding, to teach coding, and also it was an exhibition for new applications for medical purposes. And there were some other events. These are the core team of Clinician Engineer Hub. So the main plan of my presentation here was, I had an experience with 10 years, but the last 3 years was more beneficial because I could find a way to create, to show the students, the new generation, how to connect together to create something interdisciplinary. So thank you for your attention, and your if you have questions, I'm ready to answer.